ANOVA one-way classification. So till now in the previous classes we have seen what is the classification of one-way ANOVA, and next we have seen the linear model. What is the linear model? The linear model for ANOVA one-way classification is given as Yij equals to mu plus alpha I plus epsilon ij. So by using this linear model, we are going to estimate the parameters, that is mu and alpha I, by using the concept of principle of least squares, that is under the statistical analysis. So under statistical analysis, first we will be writing our null hypothesis. Then after the null hypothesis, we will be estimating the parameters mu and alpha I by using principle of least squares, that is minimizing the sum of squares of residuals. So from this linear model, we will find out the error value. So this error value we are going to use for minimizing this error. So in the last class we have, so in the principle of least square, we will partially differentiate the sum of squares of residuals with respect to the parameter. So the last class we have estimated the mu value, and from this equation we got mu hat value as y double dot bar. So this is the mean value we got for the estimated mean value we got from the first normal equation. Now consider. So now we have to differentiate partially with respect to alpha I. So next parameter is alpha I, and you have to equate it to 0. So which implies rho by rho alpha I. So what is alpha I? Alpha I represents the effect of the ith treatment. So you will be having different classes. Those classes are represented with summation I. So in each class, how many values we will be having? Ni values, and that summation will be ranging from summation over j equals to 1 to n. So here we are partially differentiating with respect to alpha I, which represents the class or treatment, and in each class we have ni observations. So that's why whatever the e value we consider, that is only over the summation j. J equals to 1 to ni, and the error value as Yij minus mu minus alpha I whole square. So since here while we are differentiating with respect to mu indicates overall mean, that's why we consider both the summations. But here alpha I indicates the ith treatment effect. So in ith treatment you will be having only n values. So whenever you are differentiating with respect to alpha I, you have to consider only the summation j equals to 1 to ni. Now differentiate it, and you have to equal it to 0, right? Yes. Now differentiate it. So similar step, this is in the form of x square, that is 2 into summation j equals to 1 to ni Yij minus mu minus alpha I into the inner differentiation value. So here this is a constant 0 minus the constant mu is also constant 0 minus alpha I differentiation is minus 1 equals to 0. Now similarly send this minus to the outside and multiply the summation over j inside. You will be getting summation over j equals to 1 to ni Yij minus summation over j equals to 1 to ni mu minus summation over j equals to 1 to ni alpha I equals to 0. Now we have to estimate the value of the alpha I. So we are differentiating with respect to alpha I. So here we will be estimating alpha I value. So send this minus alpha I to that side, so that we will before that, here alpha I, the coefficients of alpha I and mu are summation j yij minus ni into mu equals to ni into alpha I. So now here we have the mu value. So from the first normal equation, that is while differentiating with respect to mu, we got the estimated value of mu. So that mu value you can substitute here, and one more thing, here we have the formula for the ith treatment, that is yi dot bar equals to 1 by ni summation over j equals to 1 to ni yij. So if you observe this formula, in place of summation j equals to 1 to ni yij, here this value I can substitute ni into yi dot bar. So substitute that value. So here you will be getting ni into yi dot bar minus ni into mu hat. So we are going to substitute the estimated value of mu. So I am writing mu hat equals to ni alpha I. So what is the mu I value we have? Sorry, mu hat value. We have mu hat value as y double dot bar. So before that, take out ni common. If you take out ni common, we will get yi dot bar minus mu hat value is y double dot bar equals to ni into alpha I. Ni gets cancelled since mu hat equals to y double dot bar. So from the statistical analysis, before only we got the mu hat value. So ni cancel, now therefore alpha I hat, since the estimated value of alpha I, we are writing alpha I hat as yi dot bar minus y double dot bar. So now we got the mu hat value and also the alpha I hat value. So we will be substituting this mu hat and alpha I hat value in our error formula. What is our error formula? Since Eij equals to Yij minus mu minus alpha I. So substitute those values. Yij minus mu value, mu hat value, we got it as y double dot bar minus alpha I value, we got it as yi dot bar minus y double dot bar. So this is equals to Yij minus y double dot bar minus yi dot bar minus into minus plus y double dot bar. So plus y double dot bar and minus y double dot bar gets cancelled. So from this we got the Eij value equals to Yij minus yi dot bar. So we got the mu value, we got the alpha I value, we also got the epsilon ij value. So these three values now we are going to substitute in this linear model. So copy this one. So after estimating the parameters, now we substitute the estimated values in the linear model. Now the linear model becomes so what is the linear model generally? Yij equals to mu hat plus alpha I hat plus epsilon ij. Substitute the values. Yij equals to, what is the mu hat value we got? Y double dot bar plus alpha I value we got it as yi dot bar minus y double dot bar plus epsilon ij value we got it as yij minus yi equals to yi dot bar minus y double dot bar plus yij minus yi dot bar. So this is the linear model, simplified linear model we got it. Now for this linear model, I am going to do squaring on both sides and summing over ij. So squaring and summing over I and j, squaring and summing over I comma j on both sides. So for this equation, I am going to do squaring and apply the summation over I and summation over j. So first left hand side, double summation. First I equals to 1 to k, j equals to 1 to ni, yij minus y double dot bar whole square. So I have applied square in the first square term. I have applied the double summation also. Now equals to the second term here, double summation. So first I have to apply square, right? So square means for these two terms combined I have to apply the square, that is yi dot bar minus y double dot bar plus yij minus yi dot bar whole square. So squaring and summing. So summation I equals to 1 to k, j equals to 1 to ni. So now we will expand this one, since this is in the form of a plus b whole square. So we will expand by using the formula of a plus b whole square, that is a square plus b square plus 2ab. So copy this one. So left hand side remains the same. So what we have on the left hand side, that is double summation. I equals to 1 to k, j equals to 1 to ni, yij minus y double dot bar whole square equals to, so squaring a plus b whole square. So I am simultaneously applying summation also in square. First we will get a square plus b square plus 2ab and summation will be outside, right? So while expanding only, I am applying the summation also. So for the first term, summation over I equals to 1 to k, j equals to 1 to ni, a square, that is yi dot bar minus y double dot bar whole square. So this is a square plus b square, and applying summation also. I equals to 1 to k, j equals to 1 to ni, yij minus yi dot bar whole square. So this is b square plus 2ab plus 2 into double summation. I equals to 1 to k, j equals to 1 to ni, 2 into ab, that is yi dot bar minus y double dot bar into the second term yij minus yi dot bar whole square. Now we will simplify this one. LHS will be as it is. Summation I equals to 1 to k, summation j equals to 1 to ni, yij minus y double dot bar whole square equals to, write these two terms as it is. The first term second term also you write as it is. And coming to the third term, this third term will become 0. you don't remember, I'll just simplify this one. So apply the summation inside. That is summation over j equals to 1 to ni yij minus summation over j equals to 1 to ni yi dot bar. So sorry, square is not there here. Yi dot bar. Now after applying summation inside, so this one we have the formula for yi dot bar as 1 by ni summation over j yij. So in place of summation over j yij, I can write ni into yi dot bar. So this is equals to ni into yi dot bar minus, here you have yi dot bar and the summation is from j equals to 1 to n. So in place of summation j equals to 1 to ni, I can write ni directly and yi dot bar. So these both gets cancelled. So therefore summation over j equals to 1 to ni by ij minus yi dot bar is equals to 0. So this is nothing but the deviations, the square of the deviations taken from the mean value will be always 0. The square of the deviations of the observations taken from the deviations are 0. This is a property of the mean. If you don't remember the property, just go with this proof. This is the proof for that property. So if this term summation over j equals to 1 to ni yij by I dot bar whole square is 0, obviously this complete term will become 0. So that's why I have written here 0. So what is the last step we are going to get now? Copy this one. So copy all this from the video itself. So now, what is the last step we are going to get? The LHS will be as it is, that is double summation I equals to 1 to k, j equals to 1 to ni, yij minus y double dot bar whole square equals to double summation I equals to 1 to k, j equals to 1 to ni. The first term is yi dot bar minus y double dot bar whole square plus double summation I equals to 1 to k, j equals to 1 to ni. The last term is yij minus yi dot bar whole square. So now this value we are going to partition as sum of the squares. So all these values are the sum of the squares. This is also sum of the squares. This is also sum of the squares. So now we are going to write them as the partition them as the sum of the squares. So this value I am writing as TSS equals to SST plus SSE. So what does it mean? Means TSS indicates the total sum of squares. So here, TSS equals to total sum of squares. Total sum of squares. Why it is called total sum of squares? If you observe the observations, here the values, you are having the total observations are denoted with yij only, minus y double dot bar is also overall mean. So that's why this first term is called as the total sum of squares and is denoted as ST square. So what does ST square indicate? The total sum of squares. ST squares means the sum of squares. S indicates the sum of squares. Capital T indicates the total. So that's why we write ST square equals equals to, what is the value of st square? Double summation I equals to 1 to k, j equals to 1 to ni, yij minus y double dot bar whole square. So this is the total sum of squares. And next, coming to the next term we have as SST. So SST equals to, SS means sum of squares due to treatment. Sum of squares due to treatment. So since to avoid the confusion between the T's, here also total means T only you are having, treatments also it is denoted with T. So that's why for total we will be writing capital T, and for treatments we are going to write small t. So SST indicates the sum of squares due to treatment, and it is denoted as, so how you denote? You write capital S, small t. Capital S, small st square indicates sum of squares due to treatment. And this is equals to, if you observe ith treatment mean. So ith class mean, this is called as the ith class mean or the ith treatment mean. That is yi dot bar minus the overall mean whole square. So here we are having the ith treatment mean. So ith treatment minus the overall mean. So we have alpha I value also, that mu I minus mu. So that is nothing but alpha I, that is the effect due to the ith treatment. So here also in the same way we are having ith treatment mean minus the overall mean. So ith treatment mean minus overall treatment is nothing but alpha I, that is the increase or decrease in the overall output due to the effect of the ith treatment. So that's why this term is called as the sum of squares due to treatment, and it is denoted as S small t square, and this is equals to double summation over I equals to 1 to k, j equals to 1 to ni, yi dot bar minus y double dot bar whole square. Now the left out one is the last term. So this last term I am denoting as SST. So here SST means sum of squares due to error. Sum of squares due to error. So always the error, the remaining value, here it is a total, here it is a treatment. So whatever the left out term we are getting, that is called as the error here. So here we have sum of the squares of the error value, that is observed value minus ith mean value, is denoted as the error sum of squares or sum of squares due to error. So and it is denoted as so here we are writing st square. So here error means we will be writing S, error denotes with E. So SE square equals to double summation over I equals to 1 to k, summation over j equals to 1 to ni. The value is yij minus yi dot bar whole square. So this is the error sum of square. So you can write it as TSS. So the total sum of squares, whatever we got, that we have partitioned into two terms. The total sum of square will be equals to sum of squares due to treatment plus sum of squares due to error. By adding the treatment always total will be equals to treatments plus error. Suppose if you want to find the error value, how you will find the error value? The total value minus treatment value will give you the error value. So here the representation we have written as TSS, SSC and SSC, or you can also write it as, there we are writing total sum of squares. So total sum of squares TSS equals to, that can be written as treatment sum of squares or sum of squares into treatment. So if I am writing as treatment sum of squares, I will be using the notation as treatment is denoted with small t. So treatment sum of squares plus error sum of squares. Error is denoted with DSS. So always your total sum of square is equals to sum of squares due to treatment plus sum of squares due to error. So this is up to finding the partition in your sum of squares. So next we will be finding the degrees of freedom and also the mean sum of square. So total ANOVA statistical analysis has different parts. So we have completed up to some 70 part is completed, 70% part. Remaining you have still more. So till now we have written the linear model. We have performed the statistical analysis. So performing statistical analysis means we have written the null hypothesis. Next we have estimated the parameters in the model. Since we have two parameters, we have estimated those two parameters and have substituted those parameters in the linear model. So after substituting parameters, then whatever the linear model we get, for that linear model we have took the squaring and summing on both sides to find out the sum of squares. To partition the sum of squares, we took squaring and summing on both sides, so that we will be getting the total sum of square equals to treatment sum of squares plus error sum of square, whereas error will be equals to total minus treatment. So in the next class we will continue about the degrees of freedom. In the next step we will find out the degrees of freedom. After degrees of freedom we will write the mean sum of squares. So mean sum of squares means the sum of squares divided by degrees of freedom will give you the mean sum of square. After that we will write the test statistic. I said that this ANOVA will be performed by using the F statistic or the F test. So what is the F test formula we are going to get? We will find out that one. And the last we will be writing the conclusion and the ANOVA table. So copy the notes till here. In the next class we will continue with the forwarded steps.